Greetings and welcome, friends. Mr. Waddy, and should I lie? I was gonna say with my best friends in the world, but that wouldn't have been true. But we don't have to tell them, internet friends. Really, you and I are best friends. You who are watching this right now, I presume. What if I've never met you, internet friend, and then like you send me a message or a comment on this very video, and then we become best friends? That would be amazing. You could be from anywhere in the world, or maybe you don't even exist yet. Wow. Anyways, today we're going to talk about logic. That's going to be pretty great. And logic is a good thing so that the conclusions you make about life are hopefully fixed within reality rather than not. Because usually the better I understand and interpret the data that's coming into my brain through, whatever, sources I might have, the more accurately I can understand and comprehend reality, the better choices I can make about it. Because that's good. Right? If I'm processing a whole bunch of false information in my brain and then trying to live within a reality different than my brain's perception of it, that will be difficult. So one of the things we can do as mathematicians and logicians is use different types of logic or reasoning. The most basic type is what's called the law of non-contradiction, which says that, things shouldn't contradict themselves. Something is either true or false, but it can't be both at the same time. Yeah? No? Oh, I'm getting some disagreement, maybe. All right, it can't be both true and false. Contradiction, all right? So anyways, here our first type of reasoning that we're going to talk about is inductive reasoning. But before we get there, it says a conjecture is an unproven statement that is based on observations. Okay, so a conjecture. All right. You use inductive reasoning when you find a pattern. All right. Keyword is pattern when you see inductive. A pattern in specific cases, and then write a conjecture for the general case. Okay. Let me tell you a joke. Here we go. You guys ready? Here's a joke. An engineer, a physicist, and a mathematician are driving through the Scotland countryside. All right. You can close your eyes and imagine it. Here we go. It says, the engineer looks out the window and says, look, Scottish sheep are black, because he sees sheep on the hillside. All right? So that's the conclusion that the engineer says. The physicist says, no. What we can conclude is that some Scottish sheep are black. All right? And then the mathematician looked irritated and said, no. There is at least one field containing at least one sheep, which at least one side black, right? Because he's only perceiving current side of the sheep. My internet friends are ROFL-ing right now, I think. None of my real life students are, though. But yeah, in terms of like the types of conclusions we can make based on our observations, obviously the mathematician has a much more stringent worldview in terms of what types of conclusions they were comfortable with. But nonetheless, we're going to talk about patterns for a little bit here. And in example 1, you guys already have that. One of the things we'll want to be able to do is to describe the pattern and then try to complete it. And so this is a type of inductive reasoning. Here I've got a trend that I'm perhaps noticing, and I'm going to try to apply this pattern. All right, so does someone see the trend? Let's see. Describe how to sketch the fourth figure in the pattern. Your thoughts? Or could you describe what the pattern might be? It might be hard to describe. No? Nah? Although that's true from this one to this one, right? By drawing one more line here, that actually doesn't work from this one to this one. Okay, so there's another line that's added, but you then also use the word proportional. You could call these, I don't know, like slices or sectors, slices of pizza, right? Here I've got 2, a total of 2. Here I've got 4. Here I've got 6. How many slices do I expect the next one might have? 8. All right. So So I think the fourth sketch is going to have something like this, that they're going to be proportional to each other, that each slice will be congruent to the others, but also there's something else that's going on with these slices. Okay, yeah, that as far as to go from here to here to here, numerically. What about the coloration, the shading going on here? How do I know which of these 8 shade in? Maybe. So someone said the slice that's above the horizontal, so it's going to be, they're saying it's going to be one of those 4, but that's on the left. Would you say this one would work? So I might say, yeah, the leftmost one that's above the horizontal, something like that. Yeah, that I would shade this slice in right here. Yeah. So trying to describe that with words, right? The number of slices increases by 2. All the slices are the same size, and we're shading the leftmost above the horizontal slice, right? Something like that. Okay. The slice that has a side of its angle adjacent to 180 degrees. I don't know. Something. Right? So that's one of the ways you could do that. Like so. Ooh. How about this one? I wasn't going to do this one, but here's monitoring progress question 3. Let's see. So it looks like I've got 1 circle. I've got 3 circles. I've got 6 circles. Does anyone have a prediction on the next number of circles? Snowball stack here going. Saying 10. It's actually a tricky pattern to describe. I think we'd all be able to sketch it, though. How would you describe how I make my new sketch? Add 4 to the bottom, right? And then what would I add to the bottom for the next one, do you think? 5 to the bottom? Yeah. I think just, adding 2 tangent circles, right, to the bottom. Yeah, these aren't doubling. But yeah, the size of each row, right, here's 1, 2, 3, 4, add 5. Yeah, then I'd add 6, guessing like that. Question, comment? Okay. That's a tricky pattern to describe algebraically, perhaps. Maybe you've done it before. But you can. But yeah, so that's what that would end up looking like. Good. All right, making and testing a conjecture. All right, here we go. Example 2. Numbers such as 3, 4, and 5 are called consecutive integers, meaning they're side by side, one after another. Make and test a conjecture about the sum of any 3 consecutive integers. So, one of the ways I could do this is by trying to try a handful of them, right? We could try 1 plus 2 plus 3. I could try 2 plus 3 plus 4. I could try 3 plus 4 plus 5, right? And I could try to discern some sort of pattern taking place, and then maybe I might be able to describe it generically. So let's see, 1 plus 2 plus 3 is 6. 2 plus 3 is 5, plus 4 is 9. 3 plus 4, 7 plus 5 is 12. Anyone have any thoughts on this? Does anyone have a guess on this without even adding those up yet? I scribbled them out so you don't know what they are anymore. You're thinking 15? Ooh, someone's noticing this relationship that if I take the middle number and triple it, yeah? So that's a good conjecture. That so this would be our conjecture that the sum of any three consecutive integers is 3 times. Now, proving a conjecture is a lot of work. Disproving a conjecture can be really easy. All I have to do to disprove something is to come up with a counterexample. One case in which it's false, and then it's no longer a true statement. I mean, I could possibly modify it. You could, if I find a case in which it's false, I could say, oh, except for when, blah, 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 or whatever, right? Restrict my boundaries somewhat. But proving something for all possible cases, you have to know it's true for all infinitely many situations. And that's actually a little bit tricky. I mean, even if we all sat here for the rest of the school year trying to prove this true by, right, all right, I'll take the next 100, you take the next 100, you take the next 100, we actually still wouldn't be any closer to proving it true, right? Maybe we'd gain a degree of more confidence in our conjecture because, like, oh, we haven't found it to be false yet, and we tested 10,000 numbers. I don't know. But that actually doesn't yet prove it. Does anyone have thoughts on how we might be able to prove this particular one? All right, you described a variable. If I want to describe any 3 consecutive integers, the easiest ones are actually n, 1 less than n, and 1 more than n. Or y or x or whatever variable. Do you guys agree that these would be consecutive integers if the first one was an integer? Okay. You also could have done n and n plus 1 and n plus 2. But that might be a little bit weirder. That's actually harder to work with. But you could. So let's see. Let's add these things together. N minus 1 plus n plus 1. Let's simplify this. Okay? Actually, I guess I'll work this way. Let's combine like terms. N plus n plus n. 3n. And I believe, yeah, those cancel out. So I get that the sum of these 3 integers is equal to 3n, which is conveniently the way I define these 3 times the middle number. And I've just proven this for all possible integers. Right? So that works pretty well. Yeah. It is possible if I define it the other way, your cancellation or factoring, I think, has to take place. It's a little bit different, but it'll be fine. Yeah. So yeah, using variables, sometimes you can do that. Sometimes it's still quite difficult. There are still some yet to be proven conjectures out there. And in fact, Fermat's last theorem, now I'm not remembering very well. I was going to say was one, is one. There's been some, right, has it been proven? Some of the cubes or something, I don't remember, yeah. But there are some theorems, or thought to be theorems, that like have been written down in mathematical manuscripts, and then it's like we didn't have the proof for it, but the guy was writing about it as though it was true, and he's definitely proven a lot of other things in his writing. So we're like, this is probably true, but we don't know how to prove this yet, even though it was written hundreds of years ago. So that's kind of weird. But yeah, so we might come up with conjectures and then try to prove. And then our understanding in the world of mathematics grows from our perspective of it. So like I said earlier, a counterexample is just one case that disproves a conjecture. One situation that makes it false. Let's look at example 3 together here. So it can be easy to disprove something sometimes. So a student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove, right, the student's conjecture. So they said the sum of 2 numbers is always more than the greater number. Counterexample. Right, and so that's what now someone could modify their conjecture. Perfect. They could say, oh, the absolute value or the sum of any two positive numbers, right? That they might be able to restrict maybe the great grand claims that their conjecture originally made. And it might still say something that's valuable and true. It's just it wasn't as true as maybe they wanted it to be when they began, right? So yeah, so there's ways that you could kind of modify or tweak that over time. All right, this is cool, guys. This is awesome. Here we go. Deductive reasoning. This is going to be powerful. Instead of living a life based on patterns, right, we can now make logical conclusions here. So deductive reasoning isn't going to be based on patterns. It uses facts, definitions, accepted properties, and the laws of logic to form a logical argument. This is different from inductive reasoning, which uses specific examples and patterns. All right, so not patterns, okay, not examples. It's logically being deduced. All right, and here are two laws of logic. One is called the law of detachment. And so, for instance, it says, if the hypothesis of a true conditional statement is true, then the conclusion is true. All right, here we go. So let's say these things are true. Let's say that I know statement P is true. And I know that statement P implies Q is true. They're saying that I can, if I know both of these are true, that I can conclude that Q is true. All right? That's just the straight up application of if-then logic. All right? It's possible for a conditional statement to be true, but maybe I don't yet know whether or not it's hypothesis. All right? My verbal example that I thought of was, consider this. It's true that if I have a key to a lock, then I can unlock it. That's a true statement. Does that mean I can unlock every lock in the world? No. What do I need? I need the keys to those locks, right? So that statement is true, but if I still don't have the key to a particular lock, it doesn't mean I can just suddenly like, well, that if-then statement is true, so I must be able to unlock this. No. I need the hypothesis of that conditional statement to be true first. Okay? So the combination of both of those things allows me to conclude Q. All right, law of syllogism is kinds of, I call this the transitive property of logic. Does anyone remember what the transitive property was? Could restate it for us in your own words? Of equality. Yes? No? You're on the right track though. The transitive property, the side note is if man. Here, let's get if, there we go, that looks more like an F. If A equals B and B equals C, then what do you think is true? A equals C. This is called the transitive property. And I call this the transitive property of logic. Okay? That if P implies Q and Q implies R, now I can just skip the middleman, right? I can just skip these parts, and that means I know that P implies R. Now, this doesn't actually tell me whether or not P or Q or R are true. All it tells me, all it gives me is a new conditional statement. All right, for instance, with the Tuesday, Wednesday example. If today is Tuesday, then tomorrow is Wednesday. True statement. If tomorrow is Wednesday, the day after is Thursday. True statement. So I could say, if today is Tuesday, then the day after tomorrow is Thursday. That's a true statement. Even if none of those individual pieces were true, that statement is true. All right, it takes a little bit getting used to kind of that idea. Okay, So let's see. Let's use the law of detachment. This is usually the easiest one to use. You do kind of have to be familiar with these names, by the way, because I'll ask you to identify which law of logic is being used in a given example on the test. It says if two segments have the same length, then they are congruent. You know that BC is equal to XY. Use the law of detachment. What statement can you make? So here we go. If two segments have the same length, here's my P. And P implies Q, that they are congruent. I also know this particular example of P is true. So what can I conclude? This is the key to the lock. I can assume this when applied to these. Okay, so law of detachment says, all right, if BC is equal to XY, now I can say that BC is congruent to XY. The reason I can say that is the law of detachment in this case, or flashback, I could call that def of Kong, right? Definition of congruence. But I'm using this true statement here and this true hypothesis to conclude the conclusion. Yeah? Yeah? All right, let's look at example 5. Law of syllogism. If possible, use the law of syllogism to write a new conditional statement. So notice I'm going to end up with something of the form blank implies blank. I'm not going to end up with just one of their components. Okay? I'm going to end up with a new conditional statement. Okay, so it says if x squared is greater than 25, then x squared is greater than 20. They're telling me that's true. You guys believe that, by the way? Okay. If x is greater than 5, then squaring that same x is going to be bigger than or greater than 25. Is that true? Okay, let's see if I can track this here. Here's a hypothesis. Here's a conclusion. Here's that same conclusion now written as a hypothesis with a different. The law of syllogism only works if I can link one statement's conclusion to another statement's hypothesis. And because both of these match, I can now write a new statement, being, yeah. Okay? I was able to cut out the middleman and say this implied that. So what you're looking to do, just like the transitive property, you're looking to like link your trains together, and then you just make a statement about the engine in the caboose. I don't know if that helped anybody, but that's fine. All right, if a polygon is regular, then all angles in the interior of the polygon are congruent. That is a true statement. If a polygon is regular, then all its sides are congruent. That's also a true statement. Can I combine these? Yeah, the problem is they have the same hypothesis. Syllogism only works if I can link a hypothesis from one statement to a conclusion to another. What are your thoughts? That's not necessarily true, because this statement is not biconditional. Not biconditional. What we kind of have going on here is P implied two different things, but I wasn't able to like link them together. All right, so it was cool. Like, thanks for telling me, but I couldn't make any new logical leaps from there. All right, and then that was the question was, yeah, could I reverse this? And actually, that's worth pointing out. You could ask, is the converse true? Right? If I was allowed to rewrite either of those statements as its converse, and if I knew that was true, then I could use one of their converses together, law of syllogism, and link them together. But right now, I had both the same hypothesis. It only works if there's a match between the hypothesis of one and the conclusion. And even when I do that, I want to point out what I don't know. I didn't know this. I don't know x squared was greater than 20 for this problem. I cannot conclude that, because that is uncertain to me. I don't know what the value of x was. X could have been 0, x could have been pi, x could have been Google, right? I don't know. The only thing I knew was 2 statements, but none of their components. I was going to say truthiness or falsiness, and I'm going to settle with that. I'm good with that. Yep. Okay. Examples. Here's a different example. I think it's labeled example 1 again, which might break the law of non-contradiction. But here are, I forget where I even found this. It might have been like from another print of the same book. Who knows? But either way, it's flawed reasoning. So these are going to be cases in which some logical falsehood was made. Okay, so it says the syllogisms below represent common types of flawed reasoning. Explain why each conclusion is not valid. Okay, here we go. So when it rains, the ground gets wet. So that's could be rewritten as an if-then statement. I then know the ground is wet. Therefore, it must have rained. False. Why is that false? You might be thinking of the literal example they're giving us. But here, I only knew that the conclusion was true. I didn't know that the hypothesis. And this not necessarily being biconditional, right? This is the problem, that they applied the logic backwards, which in most cases you can't do. Okay? All right. If triangle ABC is equilateral, then it is isosceles. You guys think that's true, by the way? Equilateral means that all sides are congruent. Isosceles means that at least 2 sides are congruent. So yeah. Yeah. I'm then told that triangle ABC is not equilateral. What's the best way I could describe this situation? This is the same as not P. Okay? So they're saying, therefore it must not be isosceles. They're concluding not Q. Now, what I do know, I could rewrite this as, I could say not Q implies not P. I'm using implications at kind of macro levels here, sorry. The contrapositive of that statement will be true, but they were trying to say the inverse of the statement is true, which isn't necessarily true, right? So I can't do that. Can't do that. Yeah, so that's a no-go. Sometimes that works, but in most cases it works. All squares are polygons. So I think they're viewing this as not a statement, but more of like a conditional statement. Like if a figure is a square, then it is a polygon. So I'm going to break it up into if square, then polygon. They said all trapezoids are quadrilaterals. There's some if R, then nope. I'm going to run out of colors on this one. Some other conclusion. Therefore, all squares are quadrilaterals. Saying if square, then quadrilateral. Now, what's weird about this is a true statement that squares are quadrilaterals, but it does not derive from these two previous statements. Okay, this is wrong. All right, because I can't, those were four completely different hypotheses and conclusions. I couldn't link those together using the law of syllogism. They stumbled upon something that was true, but it's not true on the basis of the logic that was presented. Okay? All right, let's see. No triangles or quadrilaterals. Actually, I'm trying to think of even how to interpret. Okay. So if something's not a triangle, or if something is a triangle, then it's not a quadrilateral. Right. Well, let's see where this is going. It says some quadrilaterals are not squares. Oh man, now we're gonna get lost in the sometimes and always statements. So I can't even highlight that the same thing. So some quadrilaterals are not squares. Therefore, some squares are not triangles. I'd want to say all squares are not triangles, first of all. I don't even know how to dissect the wrongness of their logic, so that's what I'm stumbling here. Yeah. So I don't know how to analyze their wrongness any further. Let's see. Man, so much to this section and more that I wanted to get to. But I think we'll call it a day, friendly friends. Have a great day. Bye-bye.